In this lab, we're going to go through using multiple images taken at the Murillo Family Observatory at Cal State San Bernardino of Jupiter and its four largest moons, Io, Europa, Callisto, and Ganymede. So this is a two-part lab. What we're going to go through and do in this first part is to take a look at these images, measure the position of Jupiter and each of its four moons in each image, calculate the distance between Jupiter and each moon, and input those into a Google form so that we can crowdsource all of the measurements. So there are lots of images, and each person is only going to do a select few. So the first thing you want to do is go through and download the instructions or view them on Canvas so you can see them both in the assignment if you scroll down to the bottom, or you can download a PDF copy to follow along with it. There won't be anything to turn in other than your Google Forms submissions, and you'll do one submission for each image, so expect to submit more than once. Once you're taking a look at those instructions, I'll start to walk you through this process for one image and show you how we'll go through and do it. The first thing you want to do is you want to access the Google Drive folder that has the images in it. So once you click on that, it should look something like this. Up at the top, you can see that there's a spreadsheet that has image assignment in it, and then there's a whole slew of images down below. Lots. You don't have to go through and load them all. So the first thing you want to do is you're going to want to open up this spreadsheet so you can see which images are assigned to you. So if I take a look at the spreadsheet, I can see that I've been assigned one image. That's going to be the example one that I'm going to do here with you right now. And then you'll want to scroll down and find your name. Once you find your name, you'll do the image name next to that. So each person will have their own selection of images to do. So scroll down, find yours. You'll want to download those specific images. Those are the ones you're going to go through and do. So you'll want to come through here. Find your image. They have long titles through here. That's because these are the dates they were taken at the time, the temperature of the camera at the time it was taken, and then some other information there. So I'm looking for 2016. That was the year it was taken. 04. It was taken in April, on April 3rd at 5:56. So that's 5 hours, 56 minutes, 12 seconds. These times are known as Universal Time, or UT. They're not local Pacific Time. So this should be my very first image up at the top here. So I can match that name. That looks good. So to download it, I'll click the three little dots and then click Download. Once you've downloaded them to your computer, if you follow along in the instructions, you're going to open up a web browser to be able to display it. You will not be able to open these on your own local computer or even in Google. You need special software to open these images because these images are not regular images like what you take with your camera. They include an image component, but also additional text information. And we'll go through and look at both of these, but you essentially need special software to be able to open these images. They're known as FITS images for FTS. Sometimes you'll see it as FITS. And this is a proprietary format, essentially, that astronomers use for their images. So once you've gone through and downloaded it, you're going to want to open up the JS9 web browser. So essentially, this web browser is going to act like the special software that astronomers use to display and manipulate their images, but it's all done in the web browser so that you don't have to install any special software. So we want to go through and open our image. So we'll go to File and then Open Local. Once you've opened that image, you should see it displaying in the window here. And there are a few different things that we can go through and do. The very first thing we're going to do is we're going to look at what's called the header information. So this is all the text information that is that's embedded in the image itself. So the image is actually sort of a couple different files combined into one, almost like a zip file. So we're going to take a look at the header information. So if you follow along in your instructions, we're at number 4 at this point. So we're going to go to File, Display Fits header, display, and then fits header. And now this is going to open up a window that gives me a whole bunch of different information here. So there's some certain items that we want to go through and identify. The most important ones are going to be the date that we're going to go through and use. You can utilize this one right here if you want. Again, this is April 3rd, 2016, so it's month, it's year, month, day. The next piece that we're going to want for this project is going to be JD-observe, this one right here. So you'll want to save this entire long number here. And the final one that we're going to copy in here is the time observe. This one right here, which you can also realistically, it's the exact same time that was listed up here. 5 hours, 56 minutes, 13 seconds. So those are the three pieces of information that you're going to want, and you can see the date is here again as well. Again, day, month, year. This is a slightly different format, so depending on where you're looking, the month and the day are different, so make sure that you know which ones are which. These images, if we go through and take a look at them, were all taken in April. So assume everything is in April. Now, you're going to submit this, as I said before, in a Google form. So we'll go ahead and pull up that Google form. And we can start entering some of the information in now. So date of observation, again, they're all April. And we'll come back, so that was April 3rd, 2016. Next, I want that time-obs that we saw. And then lastly, the JD-obs. And you should just be able to copy and paste these directly in. That way you don't have to worry about missing any digits or anything like that. All right, so that's what we need from the header. The next piece that we're going to go through and do is we're actually going to make some measurements on our image. I'm going to first show you how to go through and adjust the image, because it can be a little challenging to figure that out on your own. So there's a few different things, and all of this is in the instructions as well in case you need a reminder. So the first thing is adjusting the image brightness. So if I bring my cursor over to the image and I click in it, I can move my mouse around while holding down my clicker button and adjust the brightness and the contrast. So right and left adjust the contrast, and up and down messes with the brightness. So at the moment, I'm going to leave it right here, and we're going to now take a look at zooming in and out, because this is not my full image right now. So if I start to zoom out, I can now see more, and if I zoom out all the way, this is the full image. So in my particular image, it looked like all 4 moons were close to Jupiter, and I'll show you what we're looking at here in just a second. But there may be some instances for your image where you have to zoom all the way out, or zoom out enough and move it around to be able to find all 4 moons. So you do need to be very careful. If you only look at the very center, then you're likely going to miss something. So I don't need it this far out. These are stars here, and if I zoom in a little bit more, even here I can see all 4 of my moons, but again, sometimes they're very far away from each other. This right here, these are 2 moons next to each other, so if I zoom in a little bit more, oops, and you're probably going to make the same mistake I did. I'm so used to clicking and dragging to be able to pan around things, but that's not what this does. That messes with the contrast. And then it could take a little while to get it back to the right view that you want. So you can see I can mess it up, mess around with the contrast and whatnot. I can still see the images, so I could leave it just fine here. So if I want to move it, I need to click a different button. Then you're going to want to go to Pan Zoom Controls. So now you can go through and change some of these numbers. Click Pan to, and you'll see that it's moved it around. I actually want it back where it was. So it's essentially saying how far off do you want to go in any particular direction. So you can utilize that if that's useful. For our particular one, we don't need to, so I'm going to leave it as it is. So the main point of this is to go through and measure the position of Jupiter and each of its 4 moons. So the way we're going to go through and do this is the software is going to go through and calculate the center of each of these objects for us. So essentially it's going to say, this is Jupiter, looking at all of the light that I'm getting here. And as I scroll through here, you can see that the green numbers are changing up top. So this number and this number correspond to the pixel location of the image. So essentially, which specific pixel are you happen to be pointing at right now? This number over here is how much light is it getting in units that are kind of arbitrary at this point. But the larger the number, the brighter it is. So if I'm over here, it's kind of black. But if I come up to Jupiter, you can see it's maxing out and it's not changing anymore. That's because it's what we call saturated. So the image, the camera has collected the maximum amount of light it can. So if you imagine that each of those pixels is a bucket, those buckets are all full of water. It doesn't matter if it's still raining. It doesn't matter if light's still shining on the camera. Those particular buckets are already full. But if I scroll over to other places, I can see that maybe others aren't. That moon happens to be, that one happens to be. So this is fairly overexposed, which is fine, because all we need to know is where the center is. So what the software is going to do is it's going to look at where the brightness levels at different places, and it's going to find the center of that for us. So in order to go through and do this, we're going to need to do 2 things. One, we're going to switch to the plugins tab over here. So this is going to end up showing us some important information once we work on the other piece. And then we're going to come over here to where it says regions, and we're going to click annulus. So that has now created 2 concentric rings here. We're going to move these rings around. They'll always stay one inside of the other. And what we're going to do is the inner circle here is where we're going to want to make sure we put whatever object it is that we're trying to find the center. And we want to do the best job we can of putting the object directly in the center. It'll calculate it for us if we're a little bit off, but if we're too far off, then it can get confused. This back part right here, it's going to give us additional information that we don't need, but it's a way to go through and figure out how much brighter is it than, say, the sky background. But the most important thing for us is that we basically just want to move it around, plop it around one of those objects, and you can see that some of my information here has changed. I have this nice picture. It looks like a big mountain. It's color-coded mountain. So this is essentially the light profile of how much light I'm getting. But what we really care about here in this particular area is where it says centroid and then X and Y. So we're going to write down that centroid X and centroid Y information, and we're going to be putting that information into the Google form. So at this point, we've got 4 moons. The question I usually get from students is, well, how do I know which one is which? Astronomers, if they were going through and doing this, would draw pictures and mark down this particular object was at this location and it had a particular brightness. So part of what this is trying to do is calculate how bright it is. So you could do that via counts, or you could do that with some other sort of calculation. But essentially, astronomers would be monitoring how bright each of these 4 moons happens to be. And the brightest one should stay roughly the brightest one. And so you kind of track, well, which one is the brightest one? And they eventually figured out which one was which, or named them accordingly. You are not going to have to go through and do that. So in your instructions, there's a link to an article by Sky and Telescope that includes an interactive tool. So if you click on this, it's going to open up this simulation right here. So this little simulation, it's got a little window here showing Jupiter, and it's labeled each of the 4 Galilean moons. So the I is for Io, C is for Callisto, E is for Europa, and G is for Ganymede. So those are the 4 moons, and it looks like this is an LO. That's actually a capital I, so Io is the name. And what you're going to want to go through and do now is you're going to want to enter in exactly the date that the object was observed at. And since this is a US one, and in fact it even pulled up the calendar, we're going to make it jump to 2016 for us. My particular image that I'm doing was from April 3rd. And then we'll want to go through and enter in the time. So if we go back and take a look at what I was putting into the Google form, or if I look at the header again, it was 5:55. So I want to enter 5 hours, 55 minutes. And then I want to go through and click calculate using entered date and time. So now we can see that it's gone through and updated for me. And looking at this, I can see that Io is actually one of the furthest away ones. Callisto is pretty close, and it's Europa and Ganymede that are super close to each other right there. And in fact, it's a little hard to see which one's which, so you can always go forward or backwards by some amount if you want, by using these plus or minus days, if that helps distinguish things for you. That's not necessarily always easy to go through and do that. But at least if I move forward enough, I can see that Ganymede is the one that was on the bottom, and Europa was the one on the top. So that means the moon that I was measuring initially must be Io. So I'm going to put down the position of Io based on the numbers that I already have. So what we need is this centroid X number. And we'll scroll down till we find Io, and we're going to put that into the Io location. Then we'll do the same thing with the Y. And now I need to go through and repeat this for each of the other moons, as well as Jupiter. So let's go ahead and do Jupiter next. So with Jupiter, clearly Jupiter's so big and so bright that it's destroying my whole 3D plot here. But again, the important thing that we need is that centroid X. And centroid Y information. So we can do this singular moon that's kind of by itself here next. And if I don't remember, I can always go back to the simulation to verify which one that was. So that moon was Callisto. So now I'll copy my X position. And my Y position for Callisto. And lastly, I need to go through and, again, figure out which one of those moons is Europa and which one is Ganymede. The system is going to have a hard time because they're so close, but we're going to do the best that we can here. So 2 things. One, we could tell that this was Io, and we could tell that this was Callisto because of how far away they are from Jupiter and because these 2 are right on top of each other. But the views of this can be flipped on an angle sometimes, and what I mean by that is if I go back and take a look at the simulation, in this little simulation it's showing Callisto as being up and Io and Europa and Ganymede being down. Now, really what I want to take away from that is that Europa being the moon sort of on top here in this view, and Ganymede being the one down below here on this view. Really what I want to think about is Europa's more on the same side as Callisto, whereas Ganymede is more on the same side as Io. So if I come back to my view here, if this is Callisto, then that means this one on sort of the bottom left is Europa, and this one on the upper right is Ganymede. So I want to make sure that I know which one's which as we're going through and doing this. So I'm going to move my annulus over to them. And I can actually resize this, so I'm going to shrink it down so that hopefully I'm getting just as close to only having one moon as possible. And it's not great, but it's the best that we can do. Okay, so I said this moon was Europa, so I'm going to put this in for Europa's information. And then I'm going to do the same thing for Ganymede and just move it over onto the other one. Now you'll see that these are really very, very close to each other. So it's a difference of a fraction of a pixel is essentially what it's giving me. So the x position for Europa is 2420.06. Ganymede is 2420.21. But that fraction of a pixel is still very important. We're gonna need and utilize that. So now that we've gone through and measured the position of all of these, next we're going to go through and we're going to calculate the distance between Jupiter and each of these moons. So I'm going to do this using Wolfram Alpha, 1 so that you can see me, and 2 so we can make sure that we get our calculations correct. You can use a calculator, whatever you want, to go through and do this. Okay, so when we're going through and doing this distance calculation, which you can see the calculation itself in the instructions, we want to make sure we do the order of all of this correctly, and we want to make sure that we're consistent as we're going through and doing it. So the first thing I'm going to start with is the square root. And then whatever I want in the square root is going to be within those parentheses. The next thing I need to do is I'm going to subtract the two x positions. So the x position of one of the moons and the x position of Jupiter. Now this order actually doesn't matter. So if you accidentally do Jupiter's x position minus a moon's x position, that's okay. We just want to make sure that we keep the x positions together and the y positions together. So I can come back over here and I can pull my values. So what I've done so far is I've got another parentheses, the x position of Io minus the x position of Jupiter, and now I need to square it. But we're not done. We need to go through and do the exact same thing for the y positions. So plus, new set of parentheses, and we'll copy and paste the y positions in as well. So now I have my formula is complete. It's giving me the information that I need. So I'm going to copy that result and I'm going to paste that in, if I scroll down here, to the distance between Jupiter and Io. You'll basically go through and repeat this for each of the moons for the positions that you have. Again, the Jupiter ones won't change, so you only need to go through and change the X and Y positions for the moon. The way that I put them in, those are the first two in each of those parentheses. Enter the final numbers in. If you don't see a moon in your image, so for example, if this one right here was a single moon and I looked everywhere and I couldn't find the other moon, then everywhere for that missing moon, let's say it was Europa, you would put in n/a, so that one, you're putting something in the form will let you submit, but two, it's obvious that there was not a moon there for you to go through and measure. We want to make sure it's something that's not numbers for our next piece. So I'm going to go ahead and take a moment and calculate these final positions, and then we'll finish things up. All right, so now that I've gone through and calculated each of the positions, before I click submit, I want to go through and do one final check, and that's to make sure that these numbers look reasonable. So when I identified the moons before, and let's go back to that simulation one last. If I look at these moons right here, I can see on the Callisto is the closest. And then Io is a reasonable way away, and it looks like maybe Europa and Ganymede are maybe a little bit further than Io. It's on the other side, so it can be a little bit difficult to tell visually. But I at least know that those two are right on top of each other, so those two should have the same distance. Something similar to Io's distance, but maybe a little bit bigger, maybe a little bit smaller. My guess is a little bit bigger. So let's go back and take a look. Do our calculated distances make sense? Is Callisto the one with the smallest distance? Do Europa and Ganymede have almost the same distance? If I don't see that, then that means there's something wrong with either my calculations or the positions that I put in. So I would want to go back and check that before I submit finally, because once I submit finally, that's it. And the whole class is going to have to use the data that I have. So if I come back over here, I can see that the moon that's closest to Jupiter is Callisto, which is good. That's what we said before. Europa and Ganymede are almost exactly the same distance. It's a difference of 0.32 versus 0.38. And then it turns out that Io was a little bit closer, according to my numbers. But all of this seems to make sense, so I'm ready to click submit. Once I go through and do that, I can click here to submit another response, because I need to do this form for every single image that was assigned to me. Once you do all of your images, again, that are listed inside the assignment sheet, then you're done. Your submissions into the Google form are the only thing needed. So I'll monitor this as things are submitted. Again, it's got your name up the top, so I know who submitted it. Make sure you use your full name. And that way I can go through and record. You did all of your submissions. I'll take a look at them, make sure that everything looks okay, and then give you credit for it. So repeat this process for each of your images, and you'll be done with this part 1 of Jupiter's Moons Lab.